And I stream it. So welcome back, everyone. So before starting today, any questions from last lecture? It was I think I mentioned that yesterday. I think it's one of the most important lectures that we have in the course. So any questions from last lecture, from Ramsey's modularity lecture or class? Okay, so today we're going to be discussing, and before that, before I forget, a couple of things. Recall that today is the deadline for the assignment at midnight. So I think you guys have, you're in good shape, at least from the questions that we have seen. It looks like you guys have everything more or less under control. Okay, let me see the chat because I have it hidden here. So Iman has a quick question for the assignment. If this is okay, do we need to use any special library to format the output test? Just spaces are fine, as Francis mentioned. So no special library is needed whatsoever for this assignment. Okay, sorry, Emma, I missed that one. Gabe, should the code be uploaded as TXT or a CC file? Well, you actually need to upload 3 files, right? You need to upload the source code. That will be a CC or CPP, whatever preference you have for the extension of the file. Then you need to upload sort of a README file. I don't remember exactly how we frame it, but it's a text file, which is basically 2 or 3 lines containing how you compile the code and basically how you run the code. Okay, that's the second file. And the third file is the results that you get. So the output that your code is going to generate, we want you to actually place it in a file, and that could be a TXT file or .dat file. Is going to be plain ASCII. So those are the 3 files. So alternatively, someone was suggesting to zip them or tar them all together. That's a good idea as well. But yeah. So we strongly encourage to use the cluster for a couple of reasons. Is likely if it runs on the cluster, it will run almost in any environment. It's an environment that is homogeneous for everyone, so everyone see the same thing, especially UofT, who is going to be grading the assignments. And so we really encourage you to run the assignment on the cluster. Having said that, this assignment is quite simple, especially because you are not using, or you may not be using special libraries. That is quite likely that if you run on your computer, it will run on the cluster. I will encourage again to try, if you develop on your own computer, to try it on the cluster, just to be sure. Okay. If we modularize it over code, I'm reading Michael's question. If we modularize it over code, we should have five files, right? 5. Correct, and depends how many modules you actually created, but at least 5. That's right, Michael. Yeah, that's right. Some of you were asking if it was mandatory or required for the assignment to modularize this assignment. We didn't ask that. We are not going to enforce that. But of course, if you want to do it, I think it's going to be good practice and for sure won't hurt you. Dargesh, is the output text the same as the Lisa Shoot text? That's right. That's exactly right. That's exactly right. No problem. Any other questions about the assignment? I think these are really good questions. Just as a reminder, if you have further questions, we do have office hours. Of course, next one is tomorrow, so it's after deadline. But we also had the forum, which has been quite active. Lately has been quiet though, but the forum is a good resource, and many of you have also the chance to answer questions there. So, you know, it's a good opportunity for everyone to have a discussion there. And if not, if you want to have a more private contact with us, you're always welcome to write to us to courses@scinet.utoronto.ca. Okay. Okay, so that was one of the things I wanted to mention, the deadline for today. Assignment 2 is going to be posted later today. We'll probably let you know by email, but it's going to be posted later today and due in a week, all right? So if there are no further questions, neither from the assignment or last lecture, then we are going to start talking about a new tool. I hope that you guys can see my slides. Is that right? Let me see if I can go full screen, because I believe you are seeing just a partial thing. Perfect. So, okay. So today we are going to be talking. Let me know if you cannot see the screens. I went full screen, so hopefully you should be able to still see the slides. Okay, awesome. So we're going to be talking about a tool that actually goes beyond the scope of C or C++ or any other language for what matters. It's a really useful tool. It's not only a tool that is important for programming and developing, but it's a tool that is within those tools that are qualified as best practices in software development or best practices in software engineering. So the tool I'm talking about in particular is Make. It's called Make, and it's a tool for automation of building things. And the building thing can be, as we're going to see in the examples, it can be almost anything. It can be code, it can be executables that you generate from source code, but it can be, for instance, papers. If you are used to write papers on LaTeX, then it can be papers generated on LaTeX, or it can be basically almost anything that can or has a process that can be automated. So I'm going to very quickly go again through the modularity part, because this tool takes full advantage of modularity. And not only that, it helps modularity a lot. So when we break the code into these different modules, into these different parts, some things can be a little bit more tricky, like for instance, the compilation part, but Make can substantially help and take advantage of that at the same time. So we're going to review that very quickly. We are going to then see the make command. We are going to see how to interact, how to basically program it. Believe it or not, it's a pseudo, let's call it pseudo programming language in itself. And then we are going to see a few examples. Okay, by all means, please feel free to ask questions if you have. I'm going to try to monitor the chat as we go along, so just feel free to ask your questions. Okay, and if you feel like I'm muting, that's fine too. So this is taken from Rancy's last class. So we went through the modularity, and as I told you a couple of times already, I think it's a very important concept to grasp and to try to understand. It will take some time if this is the first time that you hear about it, but it's substantial. It's any software development in a professional manner or any complex piece of code that you will develop will follow this pattern. And this pattern not only applies to C, Fortran, compiling languages, it applies also to scripting languages like Python or R as well. Some things will be slightly different, but the concepts still apply. So one of the things that we notice in modularity is now we have these two sets of files in addition to the main file that basically brings then all the actors together in the play, are the header files and the implementation files. And one of the nice things of breaking the code in modules is that these units now are kind of independent. So you can, in principle, take each of these units and compile it by itself. And this is also tied to the way in which the compilers work. Now you will take, or you will notice two stages in the compilation, the actual compilation where the compiler goes, take your source code from your module, and then generates an object file. An object file is nothing else than the source code translated into binary or machine code, if you believe, if you wish. And then the second stage of the compilation is linking. So linking relates to bringing together all the actors that are not part explicitly from the code that is developed in the modules. Like for instance, if you're using external libraries or external objects, all kind of things. So the linking stage brings all these objects together and then generates your final executable. And there are different ways in which you can do that. We're going to have one lecture talking about libraries. So you're going to see we can generate static libraries or dynamic linked libraries, different ways, different approaches to bring these external agents together into your executable. But why I'm mentioning this is because in this picture, there are a couple of things that are interesting to notice from the perspective of building the software that you are creating. And again, this example is very specific to C++, but please bear in mind this may apply to many other different processes of compilation or building or generation of new files or executables, if you wish. So one of the things to notice is modules can be independent from each other. For instance, and you will see this in this week assignment, we may have a module that is in charge of reading and writing files. We may have a module that is in charge of solving differential equations. We may have a module that is in charge of interpolation, and so on. So these modules, which are in principle independent, can be compiled also independently. So this allows or gives space for us to optimize the compilation. And again, you may be laughing, oh, compilation usually takes a few minutes. Well, that is true if your code is small, but for large projects, it can take several hours, if not days. So compilation can be also optimized in the way that it can run in parallel. So if these modules are truly independent, then I can compile module 1, module 2, module 3 in parallel because there are no interconnection whatsoever between them. So that's one of the things. The other thing is compilation can be cumbersome, like the way we compile the code may require to have a long list of flags and options indicated to the compiler. That is nasty and you know, it's not practical to keep writing or something. So you may have a script where you reproduce that, but may help with that in doing exactly that, but in a smarter way. And finally, the linking stage can be also cumbersome because all the linking, all the references to the external libraries has to be there. Francis also mentioned this in his lecture last time. When you link with external libraries, you not only need to include the library in the source code, but also you need to specify or indicate to the compiler which library you want to use. Where is the library located? If it is not in the path, and so on. So all those flags has to be there. And again, this can make your compilation line a little bit not trivial, let's put it that way. So having that is good. And there is a third reason I believe this can be really useful to have. We will see in a few minutes that this can be put together into a script that goes to make. So this basically represents a recipe for building the software. And if it is recorded, if it is reported in this script, that constitutes also metadata of the building process of the software. So it's a win-win situation for everyone. It will help you optimizing the compilation. It will help you remembering these cumbersome lines of compilation, but also it will keep a record of how you compile. And when you do this in a professional manner, not only that, it can help you to port and compile your code across different platforms. And there are specialized tools, other tools in parallel to make that can take advantage and basically use this approach as well. So any questions for, I know I have been talking very, very generically yet. I haven't shown you any specific example or any specific about make yet, but any questions so far? Are the ideas and the concepts that I'm talking about, do they make sense? Okay, I will assume they hope they kind of do. So let me talk a little bit about, perfect. Let me talk a little bit about Make 10. Many of the things I kind of mentioned before, the compilation of large programs basically requires two processes. First, individually compile each of the source codes and to generate these binary objects or files, and then link the objects together to generate the executable. I mentioned this, however, it can get complicated and redundant. You need to keep track of whatever dependencies are there. That's another thing I forgot to mention, but if you have dependencies, that has to be followed with track. You need to retype the entire compilation command. That can be cumbersome, as we say. It is easy to forget your compilation flags. And I tell you a brief thing that happens to me many years ago. I was writing my code. It was in Fortran, and it was a post-Newtonian code. Whoever is interested in that, but basically I forgot my optimization flags, and the code was terribly slow. And that was because my optimization flag was not there, and that changed substantially the speed at which the code was running. It was just that, and it was just one of the steps of the compilation, because it was actually the module in charge of doing the partial differential equation solve. So yeah, you don't want to forget any of your compilation flags. And as I mentioned at the end, it's better to keep all this information contained on a single file. And this is where make can help in this process. So some generalities about make. So make is a program, is a tool or utility program. It's used to build programs from multiple CPP files, source code files, header files, object files, and other files. But as I say, not only used in C or Fortran or any compiled language. You can use make with Python, R, LaTeX files, basically any task that you can generate an automatic way of processing the different steps that you have. Make is a very general and flexible, I would say, framework that is used to compile code of any type. One of the nice things of make is it can take a file, usually known or called makefile, as its input, which specifies exactly what to do and how to do it. What this makefile contains are different things. They contain variables, rules, and dependencies, and we're going to see this in more detail. It specifies also the executables, the compilation flags, and the library location if needed. It is, I mentioned this at the very beginning, it is a crucial component of professional software development. Again, if you are planning to write code that is going to be used by your research community, or just make it public on the internet, or submit to the Journal of Open Software Source Code, those are things that you need to have. Besides building programs, they can be used to manage any project where there are files that might be updated automatically due to other changes. That's another thing that make is really nice. I forgot to mention that, so let me go very quickly to this picture. Let's say this represents part of our project or our final project, and we have these different modules, but I only changed this last module here. So make, what it will do is it can take a whole look at your project and look and see which file has changed and only recompile those files. So again, that is a performance improvement. Think about, big projects where the compilation can take several hours. And if make detects that you only change your input-output module instead of the whole set of modules, then it will go recompile this module, redo the linking stage, because now it has to be redone, because it's not just plug and play. You need to rebuild this object and then regenerate the executable, but it doesn't need to go through the whole compilation of the module. So that is something that is also very nice of make. You need to use it with caution. Sometimes you get sort of false positives, in the sense that it can get confused. What it does is it look at the last timestamp of the file when it was modified and when it was compiled, the object. And sometimes it can get confused, especially if the dependencies are tricky. So there are ways to mitigate that. We're going to see how to do that in the examples. That is something to keep in mind, okay? And then there are a lot of good resources. I just placed one here for learning make, is the new make reference manual. So if you probably want to dive deeper into make, that's a good place where to start. Okay. So basic uses of make. So as I mentioned, make is a command. If you install any compilers, it should be there. If you're using your own computers, in the cluster, it's there for you as soon as you load the corresponding modules for the compilers. The way it works is again, as any command line command that we have seen. You invoke the command by typing its name, in this case make, and then there is a list of targets or in this case optional arguments, which are called targets, which can be printed or not. If you don't say anything else other than just make, then make will execute the default rules that you have in your make file. It basically builds the first target that appears in the make file, which is traditionally a symbolic funny target, name it all. We are going to see this in specifics in a second. Make will decide what targets in your list of targets are needed to be regenerated, basically by looking at the times in which were modified, and if they are objects files associated to them, if they haven't been modified, it won't regenerate it. And as I mentioned, this solves the problem of avoiding to build files which haven't been updated. Makes contain many command line arguments, and as it happens with any command in Linux, you can do make -- help, and you can see all the possible options that you can pass to make. One that is quite useful is, as we're going to see in a second, is to indicate -f and then the name of a file, because instead of make going to look for this make file by default, then you can specify a different make file name. So for instance, I have an example here. So if you do make -f my make file, then you can use a file called my makefile instead of makefile. By default, make is going to look for make files called makefile in lowercase, capital M makefile, or new makefile. All these are going to be the defaults. It may depend a little bit on the version of make that you're using, but these are, I think, by convention, the defaults that make is going to be looking for a makefile in case that you don't specify any. Now, I have been talking about the makefile. The makefile is nothing else but just a plain text file with a particular structure, and indicates the targets. Indicates that when I mean the targets is what do I want to build and how to do it, and those are called the rules. So each target has a set of rules that indicates how you build those targets. Okay, any questions so far? The other thing that you're going to notice, at least in my examples, is, and most of the people do this, is that make also allow you to include commands from the shell, from the Linux shells or the environment that you are working. So you can actually generate pipelines of processing even during a makefile, or within a makefile, I should say. So let's start to look a little bit about how the structure of a makefile looks like. And let's start by looking at what we call the rules. So basically, as I told you, a makefile consists of several rules. You can have different rules for doing different things, for targeting different things. And a rule begins with a textual dependency, basically a word, followed by a colon. Okay, so one thing you will notice is make in particular is very strict about how you need to structure your text files for using as makefiles. So in one way, you can think about if you are familiar with Python, you can think about like indentation in Python. It has to be in a particular manner. Well, this is like that, but even a little bit beyond that as well. So a target starts with a word, then followed by a colon. And optionally, you can enumerate components or file of the targets in which the target will depend. So it will say, okay, this first box here is a rule. This is going to be my target. And then there are the list of dependencies. What it means with the list of dependencies is this target need to have these other targets built before in order to succeed, in the generation of this target of this rule. Okay. And then what follows is the list of commands that you will issue in the terminal if you were doing it interactively to generate that target. And again, think about the compilation process. Think about the compilation we saw last class, like generating the object file and then linking the object file with whatever library or other modules need to be done for generating your executable. So this dependency line is arranged so that the target goes from the left of the hand column, depends on the components on the right of the hand column. So this target depends on these guys right here. It's also common to refer to these dependencies as prerequisites of the target. Same thing. Now, I was talking about the structure and the pickiness of make about that. Well, make requires that whatever are the commands associated with this target to be indented, and you cannot indent in any manner that you wish, but you have to indent using the tab. And the tab, if you're not familiar with that, is the key that looks like two arrows pointing in opposite directions, or just says tab. But basically, all the commands, when I'm showing this space here, all the commands that follows or belongs to a particular target built-in block should be indented with one tab. If you don't do that, then make is going to complain. Even if you put enough spaces to basically reach the same location as the tab, make will complain, will realize that these are spaces and not tabs, and it's going to complain about that, and you will get an error. Okay. So it's very, very picky, very, very restricted about how we structure our text file. Okay. So that's something to bear in mind. The actual error I include here, if you don't use tabs and you use spaces, the error that you will get is missing separator stop. And this is because it's not telling you explicitly you are using spaces instead of tab, but it's telling you that it can't find the symbol that it's looking for to separate the target definition from the commands to build the target. So that's what it is, and usually gives you the first line where it detects that. All right. So one first thing that we learn about make is it has targets, it has dependencies in which the targets depend upon, then it has commands to generate the targets, and the commands has must be indexed using a tab for that. Okay. So this is our first building block. A little bit more about rules. Each command is executed in a separate shell or command line interpreter instance. This may sound as a technicality, and kind of it is, but it has some practical effects. And here I'm showing you an example. So for instance, this is a makefile that its only goal is to cd into a particular directory, or at least the rule that I'm including here is to cd into a particular directory and list a list of files. So as you can see in this example in particular, I'm not compiling anything, I'm not generating anything, and just, if you wish, automating a particular action I want to do. So these two first lines here won't work. And the reason is in the comment. And by the way, make can include, and it should, as we're going to see if we have time today, it should include comments describing what you are trying to achieve. And comments are specified using the hashtag or the number symbol, okay? So these two lines of commands won't work. And the reason is each line is executed in a separate shell. So imagine that you are in, what I mean with that is, imagine that you are opening different terminals. And in one terminal, you cd into the directory where you want to look into the files. And in a separate terminal that has been opened in a different directory, you do ls. So what the result of this is, it will show the list of files that are in the terminal that you just opened, but not in the source directory where you want to go. If you want to make it work, what you need to do is, okay, cd source, nothing different, semicolon to separate commands, and then using this backslash, which means this is the next line is a continuation of the previous line. So in that case, you can read that cd src for source, in this case, semicolon ls is part of the same set of commands that are executed in a shell or in a terminal. I hope that makes sense. Commands, as I mentioned, can be separated by semicolons, and comments are included using hashtag. Another nice thing is using the @ operator or symbol results in the command not to be printed to the standard output. So you can say, for instance, this is another simple rule, hello. What I'm doing here is for the sake of space, instead of breaking the line, having a new line and tabbing, it's just on the same line I put semicolon. That's another thing you can do. I usually don't recommend doing that for clarity purposes, but I'm doing it here just for making fit on my slides. And then saying echo hello. And this will just print the hello word on the screen, but not the command, okay? So this is exactly the same as before. So instead of doing the semicolon, you can do a new line and then the tab. Now, one thing, and this allows to comment on something either in both students of these examples, is a rule may have no command line definitions, and the dependency line can consist solely of components that refers to targets. So someone joining. So an example of this, this is another example of a makefile, which basically contains several rules concatenated. So this is a typical situation you will see in many makefiles that you're used for compiling code. You usually get 3 different cleans instances. You have something called real clean, and you have something called clean, and then it can be something like this clean for distribution clean. What is going on here is that the real clean rule, in principle, may not have any command at all, but only dependencies on the clean and distribution clean rules. What it means is when make hits this real clean rule, it will say, oh, real clean depends on clean and distribution clean. Then I'm going to go and execute clean and this clean then. So you don't really need to put anything on the real clean rule other than just putting the dependencies of prerequisites, as we mentioned, which Make will interpret as, okay, you want me to execute these other rules for you. And then clean, for instance, just to give you an example, usually deletes all the objects files. And this clean may delete a tarball file that you generated to basically put together all your source code and executable if you wish. Any questions so far about this? Now we have something more substantial, more specific. So I hope that the examples are more or less clear. So far, we have seen examples that don't necessarily relate to compilation per se, but automation of different tasks or different processes that you want to do. So any questions about this?
I'm wondering if you run a rule, and it's like the dependencies have already been run once, will it rerun dependencies? Does that make sense?
Good question. Like for instance, let me be clear. In this particular case, in the clean rules, because it cannot check for the dependencies work very nicely in be redone or not if there is a file associated with it. So for instance, if one of our dependencies or prerequisites was to generate an object file, and let's say that clean, instead of deleting file, was generating an object file and made detects that that object file exists. And not only that, but the sources didn't change after the object file was generated, it won't rerun the prerequisites. Make sense?
Okay, thanks.
No problem. So yes, that's one of the nice things of Make. There is some smartness, and the smartness is related to these timestamps and object generations or file generations. Now, I had to warn you, sometimes this doesn't work, and having these clean rules is part of how we fix these issues. When the dependencies are complicated and Make cannot figure out, and we're going to see a little bit of how Make figure out these things, but when Make cannot figure out those things, then you need to have, it's always good to have these clean rules, because then you get rid of all the objects or intermediate files that you generated that are prerequisite to other rules. So sometimes you change a library or you change a module, but that module has a particular dependency or link into another module, which is not clear to Make. And so then you need to enforce the cleaning of the object files and then the regeneration of the whole intermediate files and final file as well.
Right. So,
yep.
Just to be clear, Make is like another program in its own language that just tells the computer in what order to execute the other files I want it to compile?
That's exactly right. That's exactly right. I don't think people call it like another language. It's more like a macro language because it doesn't have commands of itself. It has a set of rules and patterns that it can follow. But yes, you got the idea right. Yes. And that's why I'm saying it's not tied to C or C++. Obviously, it's one of the most well-known cases or useful cases where you can use it. But you can use with any other compile language. You can use, as I was showing you, examples of just shell scripting, if you wish, or manipulation of files or things like that. You can use, I will show you a few examples at the end of how to generate manuscripts using LaTeX, which is another language for writing papers, for instance. So you can use it for whatever you want. Okay, Rob, is Make using shell scripts essentially? I mean, you can use shell scripts, but it's more than that. I have a slide clarifying a little bit of this, but there are two things going on with make at the same time. One is make is going to build this tree of dependencies, let's put it this way. And then it's going to look at these macros. You will see makefiles can get complicated. So right now, I'm just showing you some simple examples, but it can get complicated. So there is some sort of, don't like it to call it a language per se, but it's more like a macro language, if you wish. Okay. But it may feel like shell scripting at some point. So this is a little bit of what I was talking about. So you can define also what are called macros and variables. Macros are usually referred to as variables when they hold simple strings definitions. For instance, this is a very typical situation. In many makefiles, you will see at the very beginning something like CXX equal C++. What we are saying here is the compiler I want to use is going to be C++. If you have been using Linux or the standard GNU compilers, this is the typical compiler you will get. If you switch to another type of compiler like CLang, then instead of using C++, you will be using CLang. That's why there is this definition. But more than that, by having this definition, then instead of using C++ or CLang or whatever is my preferred compiler for C++, I can just refer in the rest of the makefile to CXX instead of using C++ or CLang or ICPC if you're using the Intel compilers. So it's a way somehow to make the makefile more robust to changes. You only need to change this line to specify that the compiler you're using is a different one. And for instance, if you're using module systems like in supercomputers, many times these variables may be defined for you whenever you load the module. Now, these macros in makefile may be overridden in the command line arguments by passing specific definitions to the make utility. Macros also allow users to specify the programs and invoke another behaviors during the build process. For example, the case that we were just discussing, CXX. So in the way it works is very simple. It's like a variable definition in terms of make. It's called sometimes macro definition, but it's a word equal and then the definition. So this is another example. And again, I'm trying to keep my examples a little bit apart from the compilation itself, but you will notice that all these examples are part of, again, usual makefiles that you will find with different software. So for instance, in this case, I had 3 macros definitions and defined in different ways. So the first macro definition is the word package, and it's given by a particular string. So in this case, I call it package. It can be my package. It can be my PhD thesis, something, right? Then is the version. And notice this, I'm using some scripting or shell scripting tricks here. So these backsticks at the beginning here, trying to underline, and at the end, what it means is whatever is within those backsticks are going to be taken as a command in the shell, executed, and the result returned into a string and put into the version macro. So in this case, I'm asking for the date in a particular format. I want the date in years, month, and date. Okay. My last macro is archive, which is given by whatever is the value of package slash the value of version. So $, parentheses or curly braces, and the name of the macro or the variable is a way to refer to whatever the variable or the macro contains on the shell. So there are 3 different ways of defining a macro or a variable in make. And then comes my rule, dist for distribution. So in this case, my rule is calling the tar file, the tar command, which basically is able to combine files, and it's going to create a file with the name given by the macro archive. So in this case, it will contain the name of the package slash and the timestamp of when the make file was generated, .tar, and dot represents the current directory. So this rule, what it's going to do is it's going to expand this line to this thing, tar-cf the package, because it's the string I brought here, dash whatever is the return of this value dot tar, and basically compress, or not compress, but bundle together all the files contained in the current directory. Okay. So in one way, environment variables and macros are the same, sort of, for make. Okay. Any questions about this? So this is what I was mentioning before. Make does kind of two things at once. The first thing it does is describe a dependency graph consisting of targets and prerequisites. And insofar, I haven't shown you any, well, other than the real clean and the clean example, many dependencies. The other thing that does is a macros language for performing textual substitution. That's what we do with the macros or the variables. No, they do not need, Lucas, they don't need to be capitalized. I think it's more a convention than anything to differentiate from most of the commands. Yes. So, sorry, I may have been confused with the question. $, parentheses, or you will see sometimes curly braces. It's a way to access the value. I could have written $package. The way I usually like to do in this way, instead of using $, and the name of the variable, is because you can protect so on the one hand, it's cleaner and clear for me that you're referring to the content that is defining the package variable. Sometimes you can put underscores defining the variable. So that's why I prefer to do that way. But you could have written $archive. Okay, that's interesting. So you see, so Rances is describing that for him, I think he's in an Ubuntu machine, or are you trying on the cluster Rances? Sometimes the way the shell, any shell make, okay. Sometimes they make, the type of make that you select may not work, and depends how it's expanding the variables. So that's why this is called protecting the variable. So you know that by doing $ parentheses or curly braces will work as well. You are protecting the variable. So you are certain that you refer to this variable. So there are, like Rances is mentioning, $archive will be taken as the variable A instead of the variable archive. So you need to actually use these parentheses to say, okay, the name of my variable or my macro is archive and not just A. Okay. But yeah, that's a good point. Okay, so I had a few comments here. Some of these we have mentioned. Variables begin with $. This is something coming from the shell, but it has some adds-on in make. So it's enclosed by parentheses or braces. If you had a one single character or variable, then you don't need that. So that's why basically you do $CC for the C compiler, $C_flags for the flags that you will pass to the compiler. And then there are some automatic or special variables that make the finds for you. So for instance, we have the $add, which refers to the target file name, or $* refers to the target file name without the file extension, or $smaller than. This is the first prerequisite in the file name. This is for a given rule, of course. $hat, the file names of all prerequisites separated by spaces, and it basically discards duplicated. So this is good when you want to loop over the list of dependencies. For instance, $plus is similar to $hat, but includes the duplicates in case that you, for whatever reason you want that. $? is the file name of all prerequisites that are newer than the target, separated by spaces. So each of these automatic variables or special variable has different applications in makefiles. And this is where makefiles will start to look a little bit funny, let's say, or more not so easy to follow, because you will start to see people basically writing makefiles based upon this operator or these automatic variables, and then you need to have a clear understanding of what they mean, or a fresh understanding of what they mean. So I'm going to show you some examples, for instance. And again, I'm keeping my examples a little bit apart from the CC compilation, the C++ compilation. Another way to do funny things is to use something called suffix rules. And this is a specific rule that goes with the names of the form from to, and are used to launch actions based on files extensions. So for instance, I'm going to have suffixes that are defined as txt and HTML. And then what I'm seeing here is from HTML to TXT. And what it means is, okay, take links is sort of a converter yeah, I would say it's a tool for converting HTML files into TXT files. HTML files is the files that you usually find in web documents. So it's full of encodes and symbols that you don't necessarily understand unless you have a browser that converts them into what you see rendered in the web pages. So basically, this tool will take that and convert the file into a TXT, plain TXT file. So when you run makefile txt, what it's going to do is it's going to take this file txt and it's going to take the .html instead of the txt extension. That's what refers to the first prerequisite in this case, and then dump it with this redirection operator that we mentioned also for the assignment into the file txt, which refers to the target in this case. So this makefile, which again, in this case, if I don't show you this second line, is a little bit cryptic because it's using these operators. What it means in reality is when you call the makefile with the file name file.txt, it's going to take a file name .html and then convert into a file.txt. Okay. Now, one thing is suffix rules cannot have any prerequisites of their own because the prerequisite is sort of indicated in the from to. Okay, so that is a little bit of a restriction with respect to these rules. The other type of rules that we can have are pattern rules. Look like any ordinary rule, except that it targets contents exactly of one character. In this case, this makefile is exactly, or we have exactly the same result as the previous makefile, but in this case, we are using the percentage symbol to indicate any file containing this name. And you can see now that our rule is written in not in a from to way, but in a typical rule with dependency. So the file, whatever it is, .txt will depend on the file, whatever it is, .html. Okay, but basically the notation for how we write the rule is exactly the same, but the way that we write the rule is different, or sorry, the target is different. Okay, so again, this is a different example just to show you a little bit of what make can do. I talked about this at the very beginning, what are phony targets. Basically, a phony target is a target that does not correspond to a file or any other object. Phony targets are usually symbolic names for sequences of actions, and I have a few examples for instance, and it's also convention is not mandatory, but it's convention to name them phony. So phony variables, and then variables doesn't have any dependencies other than do something. So in this case, is echoing some variables and then the content of the variables. Another one is clean, because clean usually don't have dependencies. You could put dependencies to be sure that the file exists. So I could put all my .dat files and results.txt in my clean rule. That wouldn't be a bad idea. But in this case, I wrote my clean rule such that I'm just going to remove all the files ending in .dat and the results.txt file. This is thinking like cleaning whatever are your results. The -f flag in this case implies forcing. Some operating systems will ask you to check to confirm that you want to actually delete those files. So by using -f, you basically are enforcing that they will be deleted. Okay. So any questions about this so far? I have been showing you different examples, different ways, different features of how to make rules and how to basically implement them. And I'm going to show you how to do it with compilation itself, because as I show you, or I told you before, basically these examples are not necessarily related or doesn't necessarily work only with compilation. It works with different things you want to do. Some of the things are usually part of your makefile when you compile, like cleaning or tarring for distributing your code. But in this case, they are kind of isolated and not related to compilation whatsoever. Okay, so let's take a quick example. This is an example of a code, a little code using the GSL library. We're going to see this in more detail, but I just wanted to have an example where I need to write the code or compile the code linking with external library. So in this case, this code basically define a couple of values, so X value, and then use one of the special bezel functions from the GSL library, and basically print on the screen. There is not much going on other than just printing the value of this special bezel function and where it was evaluated and nothing else. Okay. I like to put returns in my main functions. We talked a little bit about this yesterday during office hours. Not everyone does that, but I kind of like it, and it gives you some control of what you can do with exit codes. That's why there is the return 0 at the end. Then there is the usually includes files. And in this case, my example is just one file. It's not modularized because it's not doing much actually, okay? Now, how I'm going to compile this code, where I'm going to use C++. In this case, I put the standard 11, but you can use a standard 14. It should work either way. And the thing that I'm specifying here is this -i file, flag, which specifies where to find the header files of the GSL library. So in this case, my user local include is where I install my GSL library, and that is where the compiler can find the header files for that function. So in this particular case, what the header file will have is the definition of the function, meaning what is expecting the function to obtain, what type of arguments, and what is going to return. Now, the -g flag, what it's going to do is it's going to compile the code, but it's only going to generate the object file. It's not going to link with the library yet. So this is my first line of compilation. Then the other thing I'm going to do is and I could have done this at the very beginning. Okay, I could have defined this environment variable called GSL_inc for where is the include directory of the GSL, and then specify the path to that. And when I do that, okay, instead of writing -i and the specific path, then I can do C++, the standard I use, in this case 11, I should have used 14, and then -i and the environment variable that I'm using, and then -c example C. Okay, so these two lines are exactly the same. The only difference is I'm generalizing this a little bit, because by defining this environment variable, then I can refer to the path of the location of the header files of the library by using this and not the explicit path. And you can think immediately about the advantage of this approach, because if I give you this compilation line and then I tell you just point GSL_inc to wherever you install GSL, then you don't need to specifically say where it is on the compilation line, and you can keep it generic in this way. -i, so this is Alvin, -i tells the compiler, remember this comes back to this thing of separating header files and implementation files. And for libraries works in the same manner. So you will have a header file for libraries, and some libraries are just header files. You will see examples of this in the course, but some libraries have header files where they define the functions, and then have implementation files that sometimes can be pure C code, or it can be object files that you need to link. Okay, so -i here, what it does is it tells the compiler where to go and look for the header files. Okay, I don't remember if we discussed about this before. Yes, export is used to define a variable in the terminal. That's right. Actually, you could do it without export. The thing that export does, it guarantees that remains there for the whole session. Basically, even if you do something else, if you open a new shell or something, the variable will survive that. Okay. But we're going to see, I'm showing you how to do it in the terminal first, but we're going to see how to do it in the makefile in a second. Okay, but yes, that is basically defining this variable or this macro in the main language. Now, how I will, is that clear? Let me know if there is any other questions. It's a good thing to ask about this, okay? Now, how we link with the libraries. So very similar as before, and I have a typo, I noticed here, it should be plus and 14, sorry about that. And instead of using the -I flag, I'm going to use the -L, okay? So -L specify where the actual library is located. So you notice the difference here, use a local lib or use a local include for the include files. So by doing that, I'm specifying whatever GSL library you need is in this path, okay? And then the other thing I'm specifying is that instead of using the example.c file, I'm using the example.o file, which is the object generated by this compilation here, right? Now, the other thing I'm including is the name of the library. So notice the difference. And this is -L for specifying the path where the libraries are located, -l for specifying the name of the file containing the library definitions, okay? So two different flags related to libraries linking. After that, we get our executable. But how I will do this using the same approach as before? Well, instead of defining GSL in, which is the place where we have the include files or the header files, I'm going to define GSL_lib, which is the variable pointing to where the libraries are itself. So user local lib is where I have placed my libraries here, and my linking line will look like C++, standard, at least I don't have the typo here, C++11, -L, and then the variable defining where to find the library. Then comes my object file, and then the name of the library, in this case, LGSL. So you see two different ways. One is more explicit, and depending on where you place things. Another, that dependency has been moved into a variable that you can refer in that way. Okay, so these are the first two steps. So as you can see, the compilation and linking is something that we talk about, the modularity. I'm asking you to go one step beyond and also use these environment variables where you place the location of the libraries, where you place the libraries. And now one of the nice things, again, is you are going to use the teach cluster or even Niagara. Many of the modules, what they do in principle is define these variables for you. The only thing that we do is we do it in a particular manner. So we use a convention, if you wish. So if you're using on Niagara, you're loading the GSL module, then you will use signnet _ the name of the library, in this case, GSL root, and then you can define include or you can define lib as you need. Okay. So this variable, that's why I'm emphasizing these variables that can be used, because in many supercomputers, this is the way it works. So you have these variables already defined for you. You don't really need to know explicitly where the software, where these libraries have been installed, but you have access to these variables and you can use them for your compilation lines. Okay. Any questions about this? All right. So let's take a look. So what we have done is we take this simple example. What is GSL? GSL is a library. It's called New Scientific Library, and it has a lot of mathematical definitions or scientific functions, associated definitions. The Bessel function, which is a typical function that you will find in cylindrical problems in physics, for instance, are defined there, but many more. We're going to see more details of the GSL. Yes, it's missing. Yes, you got it right. I'm missing. There should be double C. That's correct, Brandon. I'm sorry about that. So the GSL has definitions for different mathematical functions that can be useful to have. And we're going to see more details, and there are more things, more goodies in that library. I just needed an example to find that it has a dependency with external library so that we can be explicit about where this library locates. Remember from Rance's last lecture, the standard libraries are known by the compiler. So you don't need to do all this specification unless you break that standard location. But with external libraries that you need to install by yourself, that is no more the case. So you need to be very specific about where to indicate the compiler, go and look for these libraries. Okay. And yes, Brandon, I have a couple of typos here and there, and that's one of them. No problem. So I show you how to break this compilation into parts. Let's see if we can digest or work with a makefile that basically do the compilation for ourselves. So the first thing, and this is how your makefiles will start to look for compiling programs. The first thing is I'm going to define a rule to specify which is the compiler I want to use. So in this case, CXX is going to be my C++. Then I'm going to define flags or variables associated with that. So one thing that is happening here, I changed a little bit example. So I'm assuming that my CSL in this case is installed in the current directory, but I can come back and change it to this if I wish. There is this question mark equal. What that means is the shell is going to ask, is there any environment variable containing something for CSL Inc? Is this variable predefined? And if it is not, if there is no variable defined with no content, then it's going to say, okay, take the current directory. Okay. Similarly with CSL lib, is there a variable already defined in the system that points or has the name CSL lib that points to something? If it is not, then define it as the current directory. That is what these two lines are doing. Okay. That is assuming, of course, that the CSL library was installed in the current directory, which is quite unlikely, to be honest. The other thing is I'm going to define some compiler flags. That is what this nomenclature CXX, which stands for the compiler, and flags indicate. And this is going to be my -i, and then the directory where the header files are, an optimization flag. We haven't talked much about optimization flags, but this is indicating this is a no, not a 0, is -02, is optimization level 2. Then I'm going to define my linking flags. LD stands for link dynamic flags, and in that case it will be -l and the path of the library. So this is going to substitute my -l in the linking line. And then I'm going to also add the name of the libraries. And in this case, I decided to add one more library. It's not actually needed, but as you can see, it's a different program. So it's a little bit more generic. In this case, it's assuming that it's also using another library called CSL CBLAS, which is for doing linear algebra operations. So this is an example showing how to include more than one library. One library is called CSL, the other library is called CSL CBLAS. Okay, so these are my compilation and linking flags. Then come my rules. So my first target is all, and it's kind of a funny target because it doesn't have any rules at all, but it has only a dependency, and it depends on my prog. My prog is another rule, another target, which depends on the object of my prog. And it says, okay, take whatever, generate my prog, and then use my prog.o as the source, and then use the LD flags and LD flags, which are this last one here. So this is my linking line here, okay? My prog, which is the name of the rule, depends on the object file, and it will generate the executable called my prog. Now, we need the compilation line, and that is the rule called myprog.o. So that is this rule right here, depends on my prog CPP, which is the source code, and this is my compilation line. So it's the compiler, the flags for the compiler, in this case -i, the header location, and the optimization flag, -c, which is create the object file but not the executable. The object file is going to be called -o myprog.o, and this is the source code used to generate that object file, which is myprog CPP. Okay. That's correct. I could have put the standard in the compiler. Some people do it. I usually keep it in a separate flag. I forgot to put it here, but you can put it in the compiler if you wish. As I say, I put it in the CXX flags because it makes more sense to me. So the targets are kind of calling functions. The targets are kind of calling functions, so calls my prog. Yes and no. So what I don't really like the term calling functions, but you can see this as so recall these are the dependencies or prerequisites. And I guess the parallelism with calling functions can be done, but what happened here is this rule depends on this rule. So may come here and say, okay, my proc depends on my proc.o, but because this is a dependency, it's going to check, okay, my proc.o have been generated, and if it has been generated, is generated after any modifications of my proc.cpp. And if that is the case, then it won't regenerate then again. So I guess, yes, you can say that, but also with some, as I mentioned before, some smartness about how is this done. And yeah, so it's cascading down the dependencies, right? So what will happen the first time that you run this makefile is, well, this is the funny rule, it calls myproc. Then myproc will say, okay, I'm depending on myproc.o. That is a file. And because this is the first time that you're running that, that file doesn't exist. So then it goes and say, oh, myproc.o depends on myproc.cpp, and it starts from the bottom. That's correct. So it checks if it exists and if it has been changed before. That's right. That's right. Okay. Sorry, we still have a few more slides to go. I think I went slower than I was expecting. So let me just move to, so it's a very similar example. I remove a few of my comments, but what I'm doing here is having a similar makefile, but in this case, the program depends on two modules. So there is an output array.cpp and then myArray.cpp. And then what I'm going to do is I'm going to have compilation lines. I'm going to have compilation lines for output array, myArray. So this will generate the object files. You can see output array is a module by itself. It doesn't depend on anything else. And so it can be compiled only depending on output array.cpp. myArray.cpp is if you wish, the main file. And then myArray.cpp depends on myArrays.cpp, but also in the definitions, this is something interesting. This is why I want to show you this example. Depends on the definition of the functions declared on the output array header file. So now the compilation line goes very similar as before, as we described. It will generate myArray.o, and it will depend on myArray.cpp, but it needs the definitions given in the header file and on output array.h. Okay. Now this is a little bit of a convention. Make one, it will still kind of make it work, but it's good to put the dependency of the header files in the rule, because if it changes in any way, then May is aware of that. Okay. And then the linking stage, it depends on myArray.o and the output array.o, the two object files. It needs the two object files to generate the executable, which is going to be called myArray. And these are the two executables. And then all the usual linking flags and linking libraries. Okay, remember the backslash means a continuation here. So this line is continued in the next line. Okay. The other is more or less exactly the same. So you don't really need to worry about the macros definitions or environment variables definition. But I just wanted to show you a case where there are two modules instead of just one. Okay. This is a little bit of how makefile look at this. And this is, I'm sorry about the colors of the source files, output array.cpp and myArray.cpp. But let's imagine that myArray.cpp depends on the GSL and GSL-C BLAST libraries. This is the dependency tree that make look at it or creates for it. Now, the new thing that I'm adding here is something that we saw before, is a clean rule. And this clean rule basically what does is it deletes the object files, but also the executable files. Sometimes people separate this behavior in two, in a clean and real clean. The clean sometimes deletes just the executable, the real clean deletes also the objects. The reason for doing that is, as I say before, dependencies, and sometimes basically getting confused with the dependencies, like if you change something in output array.o and for whatever in output array.cpp, and for whatever reason May doesn't capture that, then the object file won't be generated. So one way to enforce that is to just say, okay, you know what, do make clean, and then we are back in business. Make is going to regenerate your object file from scratch. Again, can output array.h be in output array.o instead? I guess it could. There's no harm in putting in there. Yeah, you could put it. You mean as a dependency, right? I guess you could put it there. Yeah, it will depend as well. In any way. Will the clean commands fail if you went in and delete one of the files yourself before running? I mean, it will complain that that file doesn't exist, but it shouldn't. It won't hurt. It will. So make will continue running the thing. So it will say, okay, I didn't find output array.o if you did it by hand. So that's that. Sometimes what you do is do a star.o, and in that way you basically clean all the object files. One has to be careful, of course, with the cleaning rule. Sometimes you can delete byproducts that you don't really want, but you need to be careful. The reason why they want to remove the object files, Alvin, is, as I was saying, maybe this is a simple tree of dependencies, so there is nothing complicated going on, but it can happen that for whatever reason I change the module output array, and May didn't capture that because either the timestamp wasn't correct, or it was other dependency that you changed within output array, or you forgot to put the dependency in the dependency list. That can be another case. It's more of a bug, but it still can be a case. And then if you change something, output array.o is not being updated. So in order to force that, in order to say, okay, you know what, I really want to recreate this, you can do make clean. The other reason it could happen is a more dramatical reason is, let's say that one of your external libraries changed. There was a new version of GSL, and you know what, I installed that version. I want to recompile the whole project, but I didn't change anything at all in my source code per se, but the library changed. So how can I force, recompiling? Because if I run make it will continue telling you, you know what, you didn't change anything in your source code. Why do you want me to regenerate your executable? So one way is, of course, you can always do it by hand, remove your object files, and then and the executable, because actually May will check for the executable as the final product. But then you need to remove also the object files if you want them to be recreated and be linked with the new version of the library. So there are different circumstances in one you may want to have that. It's always a good idea to have one indeed. Okay, let me see. And the way it will work is you just run make clean and then make again, and the whole executable is going to be regenerated. Okay, the other good thing that Make can do for us is parallel execution or optimization. Basically, Make by default will execute one recipe at the time, waiting to finish before executing another. However, if you indicate -shay and a number or -shops, it tends Make to execute many recipes simultaneously. If you put a number, this is the number of recipes or rules that you will execute. If there is nothing after -shay, then there is no limits on the number of shop slots, and it will try to take the number of cores that you may have, or even more. There are ways to inhibit that. So you can put, if you have dependencies, and this goes into the type of bugs that you can incur when you have parallel programming or parallel processing. In this case, you can put something like dots not parallel. So it's a pseudo target in this case. So it will not parallelize. It will not do a parallel branch of the rules in this case. So ways to control the parallel execution. Okay, quick summary. Because we are way past time, and apologize for that. Make is an utility, is an automation tool, as I mentioned. I will say it's mandatory in software development. It's widely used in software installation. It's not only used in software compilation, but also paper generation. And there are a couple of alternatives to Make. One of the most well-known ones is CMake, and that is because it allows you to to take different platforms, different operating systems, and basically run your makefile across different platforms. And that's why the cross-platform, the C of CMake comes from that. Just a little bit of context here. We talk about best practices on scientific software development. We talk about modularity. Today we talk about automation building tools. And what comes after, or in the next lectures, is version control, defensive programming. I'm not sure we are going to be talking about much about that, but certainly we are going to be talking about unit testing. So you can see these are the main foundations of professional software development, and that is what we are trying to discuss in these few lectures. Now, I still have a few more slides, which we are not going to go through, but are examples about using Make for LaTeX documents, for generating LaTeX documents, and for self-documenting helps in Make files. So I'll tell you what, we can talk about this if you guys are interested tomorrow in the office hours. And we can talk also about the documentation part that I was going to present, but again, we ran way out of time. And we can record those if you guys are interested, and then you can watch it later. All right, so I apologize again for taking too long this time. I guess I spoke too much and too slowly, or not too slowly, but too much. But again, these are interesting topics and useful topics, so I hope you can bear with me about that. Tomorrow we are planning also to go through the assignment. So again, it's a good, probably we are going to record that and then post as a tutorial or something, because the assignment will have a code that we're going to provide you, and maybe it's a good idea to go through the code together just that you guys understand that. All right. Again, my sincere apologies for taking too long, and I'm still happy to take any questions if you guys have any. No problem. My pleasure, guys. So we will see you tomorrow then during office hours.